So welcome to the last class. Do you guys see the PowerPoint slide right there? Or do you see the presentation?
I think it's the presentation.
Okay, good. So this is the question that you had for the homework, and a bunch of you got the right answer. A few of you got a factor of 2 off. I'm not sure where it went. But once you plug it in, this 36 and this 29, the estimate that you get from classical physics is 4 masses of the sun. So that's the amount of gravitational, that's the amount of energy that was spent in 0.1 of a second. So, so let's talk about black holes. Let's see, let me make, yeah. So what I wanted to do, let's make this tiny. Yeah. So I wanted to first talk a little bit about black holes and make sure that if there's any questions from you guys, we can talk about it. I mean, this is supposed to be a fun class, so ask questions, so it's fun. So what is it about a black hole that makes it black, right? Anybody?
The gravity is so high that light can't escape.
Exactly. So one of the things that you might ask yourself is, if this is a black hole, how come people were able to see it? So I don't know if you follow the news, but a couple of years ago, somebody was able to image a black hole. And in fact, here is the picture that everybody probably has seen already, right? This is a picture of a supermassive black hole in a galaxy. So how is it that they were able to obtain this picture if a black hole is supposed to be black? Anybody?
Isn't it the radiation like coming off of it around it?
Yeah,
That's
pictured. It. And actually, this is what this picture is here for. This pretty picture here is showing you all of the things that are happening near the black hole. So one thing that you can think about is, what is really a black hole, right? So the idea of a black hole is that it's so compact, its mass is concentrated over such a very small volume. And we assume that this volume is spherical, right? Because that's what gives you the best energy for compact things. So for instance, if the Earth, when you're standing on the Earth's surface, the radius of the Earth is so large that at the surface of the Earth, you only feel a g of acceleration towards the center of the Earth, right? So if you have an object that is the same mass as the Earth, but it was about an inch across, instead of the 6,000 kilometers in radius that the Earth is, this is now in radius half an inch, you actually get the conditions to get a black hole. So it's not, you can imagine how concentrated it is, right? So it's not that there's anything different about the mass inside the black hole, it's just that it's more concentrated. So yeah, a black hole with the mass of the Earth would be about less than an inch across. So now let's say that you had a black hole that was that size, right? 1 inch across black hole. If this black hole and you were 6,000 kilometers away from it, like the surface of the Earth away from Earth, from that black hole, you actually would feel the same gravitational pull as if you were in the Earth, because you have the same mass, the same distance from the center. So the black hole wouldn't pull you stronger than that. In fact, you would be able to fly away. You would just need to have the rocket to do that just as before. Does that make sense? So now, black holes are usually not that small, at least not the ones that have been discovered so far. One thing that happens is that we probably wouldn't be able to see such a small black hole, right? I mean, we would feel this gravitational thing, but it's so tiny that nobody can see it. And there's something called dark matter. Anybody knows what dark matter is? Christian? Do you know what dark matter is?
It's like matter we can't see. It accounts for like half of all matter or something.
Yeah, so what happened is that, so everything that we see it because of the electromagnetic radiation it emits, right? So now if you had matter that doesn't interact with light, it would be dark. But actually nobody knows what it is. We just know that it's supposed to be there because things don't make sense. And when somebody said like, well, if there was this much more matter in the universe, so 5% of the mass that we can account for by stars, planets, interstellar dust, things like that, is probably like around 5% or maybe a little bit more of the mass in the universe that is needed for the gravitational strength to be there to keep the galaxies together. And what happened is that people started taking, like for instance, taking pictures of how far the stars in a galaxy are orbiting around. And they said, this doesn't make sense because the center of this galaxy should be this more massive in order for the stars to be traveling at this speed. So it's just a fudge factor that we don't know what's happening. And we say like, well, if there was this much more matter that is not interacting with electromagnetic waves, then we can explain things. And then it became dark matter. So one of the theories is that there's a bunch of super tiny black holes flying around, and that would account with that for that dark matter because they would be really hard to detect, right? Like imagine you have a little black hole flying around like that. So that's a possibility. Nobody has really discovered one, but it doesn't mean that it doesn't exist. All right, so now that we talked about this, the black hole doesn't pull more strongly than any other object of the same mass, right? The thing is that, for instance, if you're far away from it, you won't fall into a black hole, just like you won't fall into a star or a planet if you're at the right distance, right? But what happens is that some of the black holes, especially the ones that are inside of in the center of the galaxy, those are humongous. So that's the thing that we see here, more or less. So we know that there's an event horizon, there's the singularity somewhere here, but then there's also an event horizon that is where light cannot escape. Not even light can escape from this portion around the singularity, right? Like the event horizon. So this is their outer surface, the event horizon. It's not a solid surface to say it like that. It's more like then, because we don't actually know what's inside, right? But you could imagine that there's a singularity where everything is concentrated in a single point. That's why it's called a singularity. But what the thing that is at that event horizon could be that this is just normal space, except that light cannot escape out of it. So it's not a real proper surface. It's just that the light around there, it will never reach out anything outside of the black hole. So it doesn't even emit light. So that's basically the definition of a black hole, an object that is so compact, that is surrounded by some mathematical surface, this event horizon, that nothing can escape out of that surface. And nobody understands what it's inside of it. Nobody knows. You can position a lot of stuff on it. You can make your own theories, and there's no way to prove it wrong or correct, right? So now the question becomes, this is the black hole and nothing escapes from it. So what is it that we saw? If nothing, not even light can escape from it. And what happened is that you don't observe directly the black hole because they don't emit any light. What happens is that there's always gas around something. In the outer space, there's interstellar gas floating around. And if this gas is close enough so that gravity is pulling on it, right, it's falling into the black hole. And it's falling so fast, it's falling into the black hole so fast that it's basically going super fast. The gas molecules that are there, so this is interstellar gas, so it's not a lot of density to it, it's very tenuous, almost kind of like vacuum, but this is moving so fast that when it collides with each other, it actually gets to 1,000,000 degrees of temperature or higher. So what happens when you take something and heat it up? Like, let's say you have a fork, right? Or you see it with coals in your grill. What happens to it when you heat it up? You see that when a metal is heated, it starts to shine, right? You can get like a little reddishness. You know that a metal is really hot when it's red. And if it was yellow or whitish glowing, you know that it's super hot. So what you see here is that the gas is being accelerated and is going so fast that it emits light because it's super hot. And that's this accretion disk. And that's the light that we would see. Any questions about that? So based on this picture, this is the light that we would see, right? And then let me move to the next picture. This is an actual image that was generated. Was super complicated to generate it, but this is the actual creation disk of the M87 black hole. So the Event Horizon Telescope collaboration did this. And to do this, they had to collect data, radio telescope data from a lot of different places and make sure that it was all coming together. So any questions about this stuff right here? Is it clear how this image, what it is actually, and then what is this little shadow in the center? All right, so the other thing that can happen is that you can have a black hole that has this relativistic jet coming out of it. So this is the other observation that people have done of black holes. So this one is really nice because you actually see the shadow of where the black hole is, right? And now in previous to that, what people had looked at is that you have a supermassive black hole, and they had been looking at it with X-ray light. And then they saw that this kind of center of a galaxy, like they went into a galaxy, they looked at it, and they saw that they could see X-ray light being emitted, and that light was coming and going. So let me show you the next picture right here. So you guys see the animation there, right? And I hope it works well on Zoom. All right, so in this little square down here, that's the optical image on the white and black with little blue dots, and that's actually a galaxy. This is a galaxy. It's called the GSN 069 galaxy, and people were studying this galaxy, and they were looking at it, and they could see that it would emit X-rays from this system, just like, and this is the X-ray being emitted, like the signal over time is what you see here on the X-ray inset. That red pulse that comes out and in, out and in, out and in. So actually that thing right there is this relativistic jet coming out of the black hole. And what people assume it was is that a star was very close to a black hole in that center of the galaxy. And when it was passing by, so imagine that here's the black hole and then there's a star and it's orbiting around it, right? When it's orbiting, maybe its orbit is not a perfect circle going around in a equal distance from it, but it actually could come very close to it as it's orbiting around it like this. And when it's very close, the star is very close to the black hole, then a bunch of the matter from the star was pulled away by the black hole and was eaten by the black hole. And then this star was coming back again and again and again as it's orbiting around. And when it's very close, a lot of its matter gets ripped out of it. And then you see this X-ray signal coming out. And it has a periodicity of the orbiting of that star. So back in 2010, they stopped seeing that signal. And that's when they said that the scientists, the astronomers that came up with this, they said that the star got close enough and lost enough matter so that every time that it was passing by, it was losing matter, but it was actually losing matter, and it made it seem so that it was coming closer and closer to the black hole until it got too close and it has less matter for it, and then the black hole just ripped it apart. And anytime that a lot of matter was coming in and it was falling into the black hole, it was heated up so high that it was able to emit light. And this is the X-ray light coming out of it, just like this. So this relativistic jet has to do with that. Any questions? All right, so then they can measure how much light is being emitted and then make estimates of how much matter was consumed by the black hole so that all of this relativistic jet was coming out. All right, so the next thing I wanted to talk about, something that you hear about is Hawking's radiation. Anybody knows what Hawking's radiation is? Jared, you ever heard of that?
I've heard of it. Isn't it? It's some kind of radiation that can it's able to radiate energy away from the inside of the black hole.
Right. So in quantum mechanics, so black holes are in our universe, and in the universe we have quantum mechanics. One of the biggest issues that we have with the laws of gravity is that nobody has made, well, a lot of people have tried and have their own theories, but there's no acceptable to everybody theory of quantum gravity. So Einstein came up with general relativity, and that general relativity is very good, except at very small distances, right? That's where quantum rules. And nobody has been able to put together the two, but there's people like Hawkins who have been working in that field, in that area. And one of the things is that in the vacuum, due to quantum mechanics, it's not really empty. What happens is that you have particles and antiparticles popping up every time. So let's say that you think that it's empty. It's actually things pop up and disappear, pop out of thin air and disappear when they got close to each other. So if you have a particle like an electron and you have a particle like a positron, the positron is the anti-electron, right? It's exactly the same properties that the electron has, except is made out of antimatter and its charge is positive. So an electron and a positron can just pop out of the emptiness, they last for a picosecond, like something ridiculous in time, right? Like it could be 10 to the negative 15 of a second, and then they go back together. And these are called vacuum fluctuations. And those happen in due to quantum mechanics, and the nature of quantum mechanics has to do with the uncertainty principle, basically. So one of the things that Hawkins came up with is that he said that if you have a black hole, and imagine that near the event horizon, an electron and a positron pop up due to quantum mechanics. So all of a sudden, these two pop out, and then the black hole swallows one of them. And then this electron doesn't have his partner, his antimatter partner, to annihilate with back forth because the black hole took it away, and this electron radiates away. Because the electron can escape because he's not inside the horizon, right? So he's just traveling fast enough, the two pop up, one goes into the black hole, the other one goes in this direction. And basically Hawking was proving that out of nothing, this black hole radiated some matter. And this is the Hawkins radiation that we have Hawkins to think about, Stephen Hawkins. So once you have Hawkins radiation, now you get that the black hole is actually not completely black because it has some thermal radiation coming out of it due to the fluctuations of the vacuum. And in fact, if the black hole is too tiny, it's going to evaporate away because it's going to be generating more radiation than what is able to. So that radiation that gets emitted, it has to balance with something else, right? So the black hole starts radiating itself away, and that might be a way that very tiny black holes don't survive for long. All right. So now for another thing that I wanted to cover. How many of you are, let me make a poll. So how many of you are Star Trek fans? All right, so not the majority of you. Why not? No, I'm just kidding. So for those of you that are Star Trek fans, how does the warp drive work in Star Trek? Anybody knows? Arthur, do you know?
The warp drive?
Yeah. You know what it is? I don't know if you're
Uh,
one of the fans of the Star
I
Trek.
think I'm not sure. Does it like move the space instead of the matter around the ship or something like that?
Yeah, that's the idea behind it. So in science fiction, I don't know, how many of you are science fiction fans? Maybe that's a good question for you to answer. Are you a science fiction fan? And there's the poll. All right, so 6-2, science fiction fan wins. One of the things that happens is that Einstein in general, and well, special relativity too, but in general relativity, said that that nothing can travel faster than the speed of light. And in this case, by nothing, he meant information or matter or even light, right? There's things that can travel. For instance, the universe is expanding and it's expanding faster than the speed of light. So that means that we can go and look all the way back And if we look back, supposedly, you could look at 15 billion light years away, because that's the age of the universe. But the other thing that people have realized is that the universe, if it started as a single point and then form a big bang, during that expansion, it has reached about 75 billion light years in length. So that's the current size of the universe. But we only get to see 15 billion, right? So it's this big, but from our point of view, it's only this big because we won't get to see this stuff that is outside of our radius of time that we have existed for, or the light that reaches us from the beginning of the universe. So that shows that the universe is expanding faster than the speed of light, but no information is going to get to us from places outside of our radius. So in reality, we're confined to this, whatever size of the light years, in light years of how much time has passed in the beginning of the universe. So there are things that, there's nothing that can travel faster than the speed of light. That's what we think Einstein said. But in reality, what he said is that nothing can travel across space-time faster than the speed of light. And then that's where science fiction writers have come up and said like, oh, then if, like for instance, even if you make a spaceship that could travel at the speed of light, it would take a really long time, like 100,000 years, to just cover our galaxy. So if you want it to be like in Star Wars or Star Trek or other series, I don't know what you guys might like, that they travel back and forth planets, right? And it takes very little time. They have to travel faster than the speed of light. Otherwise, they won't be able to make it alive across the, and then time is really weird, right? Because in movies, like they don't really explain how this works. So early on, people said, okay, so if we can get across space-time faster, then it could work. And that's not against the rules of general relativity. So for instance, how many of you have seen the interstellar part where one of the astronauts explains to the main character how you can travel from one end of the galaxy to another through the black hole? You guys have seen Interstellar, I assume, or at least 6 of you. Yeah, Jared? Go ahead. Okay, you were just voting yes? All right. So in the movie Interstellar, what he says is that you would take, so you have a point here and you start over here, right? And then he says, instead of traveling across like this, where you go from one end to the other, the astronaut tells Matthew McConaughey, what you could do is fold a space-time and go from here to here. And now you're on top of that position and you don't have to travel. So this folding of a space-time is the way that they explain in movies, Interstellar, how you could travel across the galaxy between solar systems in a few seconds. So I like that explanation. And actually they got somebody that got a Nobel Prize to be their scientific advisor for this movie. He's a professor at Caltech, Kip Thorne. And he explained that to the people writing the story, how it could work. The only problem is how do you fall into the black hole, right? And survive, but that's science fiction. But since nobody knows how black holes work and what's inside of the event horizon, you can come up with whatever you want. And in this case, they're coming up with saying that you're connecting through a space-time, that the black hole is a wormhole that can connect different points in the space-time. And maybe that's true, maybe that's how they work, but we won't know until somebody does the experiment. So if you look at movies like Avengers, Thor is also using a wormhole, right? You guys know the name of that bridge that he uses? I forgot what it's called. But Thor is traveling through a wormhole back and forth. The Bifrost, right? That's what it's called. So now for the warp drives, what somebody that came up with this idea of warp drive was thinking is that what if you could make it so that a space-time that is kind of flat, you could make it so that the space-time in front of you gets compressed, but the space-time behind you gets extended. And that was the idea that was used by early, like in the 30s and 40s, when they were writing the science fiction ideas of how to travel between space, and they have like fusion drives and warp drives and all of that. And I think that Star Trek is the first one that came up with the warp drive as used in a television or movie, but it had been in other literary works. So then somebody, his name is Miguel Alcubierre, in the 90s, he's doing his PhD in physics, right? And he starts thinking about general relativity, and he's a fan of Star Trek, and he realizes that, yeah, this could happen. And he figures out that the math does not preclude you from compressing a space-time. And in fact, what you have seen recently is that these gravitational waves, when two black holes collided into each other, those two black holes spent 4 solar masses in energy, 3 solar masses in energy to compress a space-time. And that wave of compression even reached to us. So the idea that you can compress or stretch a space-time is doable, right? And that's what we saw with LIGO. So this guy back in the 90s said like, yeah, you can do it. And here is a picture of what he's thinking, that you can make a little bubble that, and this is in 2 dimensions, that is stretching and compressing a space. So if you stretch the space in front of you, if you compress the space in front of you, you don't have to travel faster than the speed of light to cover, let's say, this much distance. You just have to bring the 2 closer together, and then you can travel at normal speed. And then you can get across really long distances like that. And he has the math to prove that you could do that according to, I mean, just math, right? That according to the general relativity, the math says this can be done, and you can make this kind of shell bubble of material and then compress a space-time in front of you so that you get to the place that you wanted to get there fast. So what Alcubierre did is that he showed that the warp drive from Star Trek is theoretically possible. The only thing that happened is that how do you make it so that you can fold the space-time like that, right? That you're compressing it in front of you so that you can travel faster in that direction. And at the same time, you're stretching it behind you so that things work correctly. So when he did this work, he showed that the math was there, but then he said that you would need either something that hasn't been observed yet, that is called negative mass. So for instance, let me show you a picture. So here's a picture. And in this picture, we have the Earth, right? And the Earth is made of normal mass. And the idea is that normal mass is just going to bend the space-time around it. So if you had a negative mass, which has never been discovered, you could make it so that this negative mass Earth, I mean, it's just a theoretical possibility, actually, instead of making a space, pulling on space like that, is bunching it up like that. Does that make sense? So that's what negative mass would do. Doesn't exist though, so far. So another thing that could happen is that you actually create a negative energy density to make the same effect that this negative mass would do. And how would you make a negative energy density? So what I talked to you guys about was this Hawking's radiation, right? That you have particle, antiparticle. Then because one of them got sucked away, the other one was left behind. That actually made it so that energy density is negative. The creation of that particle is a negative density, negative energy density around that portion of a space-time. So if you, what Alcubierre said, like, okay, if we could somehow engineer so that you make a bubble like this, that the negative energy is such that you can then bend the space-time around the bubble, then it could work. The only problem is that to generate enough negative energy, you would need a lot of matter. So one of the first paper that was written said that to make a bubble that was about 100 meters, it would require the mass of the visible universe to make that negative energy density. So basically you have to eat the visible energy just to be able to create the warp drive bubble. Then a few years later, other physicists were playing with the same ideas. They decided, oh, this is just one of the possible solutions. We can do other solutions. And one guy even said that you could probably, if you increase the volume of the bubble without changing the surface area, you could reduce the energy requirements of this space-time bubble for the warp drive. And it could be maybe the mass of Jupiter or the mass of the sun. And that's how you might be able to create these space-time bubbles. And then there's a couple of recent papers where people are still solving this. And what they're doing is that they're solving the math, right? They don't know the exact way that things work to make them. Like they're not engineers, they're just mathematicians, physicists and mathematicians, theoretical physicists that don't have any clue how to do it. They just know that according to math, if you have this equation and you want this answer, these are the parameters that you will put over here to create that answer. But they have shown that maybe you don't even need negative energy. So there's a couple of papers in physics in real journals. It's not in funny business that conspiracy theory nuts made it. It's actual physicists that they came up with other solutions where they said like, oh, you could try this and this and this as the space-time metric. And now you have some mathematical models that don't require as much mass. So maybe in the next few years, somebody comes up with a way to make this a reality, right? In fact, even NASA has been trying to make this negative energy density fields to see if those would be possible and see if there's other ways to make rocket propulsion possible. All right, so any questions about this? So this is kind of crazy, right? That very science fiction-y, but maybe it could work somehow, maybe. Or at least we won't know, right, in our lifetime. Unless one of you comes up with it. So any questions? All right, so if there's no questions, then let me close this. And come back over here. Oh, there's a couple of things in the chat. Yeah, the Bifrost, okay. So one of the most important things about this class is the experience that you guys have. So I know that this class due to COVID, we have not been able to meet in person. In fact, I don't know what you guys look like. So if I see you on the street, well, actually, I didn't see you because I don't know what you guys look like. But one of the things is that we didn't get to interact as much as if we were in the classroom, and we would have done more of the work, hands-on work, I think, if we were in the classroom. But aside from that, one of the aspects is that you get a different point of view of what physics is than what you're doing just with regular classes. So I hope that that was accomplished. So one of the ways that I get to see how you guys like the class is through the evaluations. And I would appreciate it if you guys go into the Canvas website and find the evaluations for the class and put in your evaluations for me. Especially, you can tell me if you like the topics covered or if you think that the topics were not to your liking. If you tell me the class sucks, then I don't know what to fix, right? But if you tell me maybe we should see more quantum mechanics, I'll be happy to incorporate quantum mechanics instead of whatever topic we could skip from general relativity. And then, as far as I know, it used to be that the Honors College had an evaluation, but I didn't get an email about where that one was. So if you guys know, has anybody done a Honors College evaluation? There used to be separate, but I don't know if they're using the same one from our departmental one.
When I did the evaluation for this course, it was like it was on the same page.
Both for the honors and for the department?
It was for this class and then also just as an honors class. I don't know if that's what you're talking about.
Yeah, so it used to be that we had, so when we do it in person, we used to have the honors one was online. And then we had our departmental that was in a piece of paper. But maybe they're using the same. So if you guys go and do the evaluation and you don't have any other emails, which I haven't seen, that says that this is the evaluation for the honors class, maybe there's a different one that I haven't seen. So if you guys see that one, also please fill it up. And then that way I know what works, what doesn't work. If you guys would like to do more homework, you can put that in there. If you guys think that the homework was too much, you can put that in there, especially any constructive criticism is very welcome, okay? Well, I hope you enjoy the class. This is it for us today. No homework today. If you have questions, feel free to send me an email, shoot me an email. I'll be happy to answer any of your questions if you have any. Or if you just want to talk physics, you can stop by my office and we can discuss things like that anytime. So yeah, just do the evaluation. If you haven't submitted the last homework assignment, please do so. And there's nothing else to do. I think that everybody is doing really well in the class, so that there's no need for anybody to get lower than a B at this point. But if you were to have missed assignments and you need to do something to increase your grade, I'll let you know, okay? Anything else?